Hi again, everyone. Welcome to part 2 of a lecture covering the specific effects on metals due to temperature. In this part, I'll cover what happens to metals after they've solidified as it applies to inelastic behavior. Specifically, what diffusion does to the strengthening methods described in earlier lectures. In part 1, I made a pretty clear case for how diffusion is amplified exponentially with increases to temperature. When juxtaposed against the strengthening mechanisms of metallic materials already covered in earlier lectures, it's pretty apparent how this can affect transformation, i.e. phase changes, precipitation, and solid solution strengthening. If diffusion is denied, then there is diminished ability for phase changes to occur, at least as described by equilibrium conditions. When developing precipitates by aging processes, the longer at an aging temperature will evolve larger precipitates, which may affect the overall dislocation dynamics. For solid solution strengthening, denying an even distribution of alloying ingredients will also do the same. In this part of the lecture, I'm going to cover how exposure to elevated temperatures can specifically affect strain hardening and grain size approaches to strengthening. By way of doing so, I will also provide an explanation for the practices carried out by blacksmiths. We already know that elevated temperatures can affect the overall plastic behavior of metals. But is the practice of a blacksmith specifically explained? Watching a blacksmith in order to deliver bulk plastic deformation, there can be multiple instances where the workpiece is heated, hammered, and then returned to the heat source to be hammered back out again to achieve bulk deformation. Careful observation will also identify that there's a point where there are diminishing returns on strikes with a hammer versus deformation, which acts as an indicator that it needs to be heated again. In this part of the lecture, I'll identify the mechanisms behind this. We need to first start with what grain boundaries overall do to a metal from a diffusional sense. In part 1, it was presented that an increase in temperature dramatically increases the number of vacancies within a monolithic crystal. In the instance of a polycrystal, however, there are already an elevated number of vacancies occurring at grain boundaries. This is because there are inconsistencies in the packing between grains. This discontinuity and the limited number of packing orientations, as per the crystal type, can create a wide range of free volume in a polycrystal. The grain boundaries, due to the free space available, can become motorways to transport of both interstitial and substitutional atoms. On the right, I've shown the effect of the diffusion coefficient attributed to hydrogen moving through pure nickel. Atomic hydrogen is very small relative to the size of nickel. There is a decrease of 2 orders of magnitude in diffusion coefficient over 5 orders of magnitude change in the grain size. So it's pretty clear there are big changes in diffusional transport depending on grain size. And this type of relationship is true not just for interstitial diffusion, but also substitutional because of the additional vacancies that occur at grain boundaries. We'll come back to this in a moment in terms of what it means for strength. But let's first look at what happens to strain hardening with elevated temperatures. If you recall, both edge and screw dislocations can interact when they are brought into each other's influence on the basis of their strain fields. Here I'm showing an edge dislocation as they're easier to depict, but the same thing happens for screw and mixed dislocations. If there are dislocations with opposite sign that interact, then both dislocations will be cancelled. We know that dislocations require shear applied to lattice to move. As temperature is increased, then there are unbalanced internal stresses that can cause this to happen. This is a topic that I will cover in a subsequent lecture. For now, just bear in mind that exposing a metal to an increase in temperature results in dislocation movement. Starting off with a lattice that has a mix of dislocations with both orientations, increasing temperature allows negative and positive dislocations to interact and cancel. Bends and jogs in the lattice, which were permitted by these dislocations, are still maintained by the bulk positive types. The combination of positive and negative dislocations reduces the overall dislocation density slightly. However, these are largely redundant in terms of the overall arrangement required to maintain the shape of the crystal. Further holding at temperature, the lattice will polygonize. That is, dislocations which are left behind arrange themselves to create a more regularized lattice. This process, which goes on at elevated temperatures, is called recovery. In this process, the microstructure is largely preserved. However, the dislocation density slightly decreases. There is some relief of internal stresses, but the mechanical properties of the material do not change significantly. Let's have a look at what happens at the grain level. What I'm showing here is a grain level depiction of what happens at the beginning and end of recovery. The polygonization of the lattice occurs within a grain. This is a higher ordering of dislocations in order to preserve the grain shape. If we increase the temperature further, then there will need to be further reordering of the lattice. At the sites of polygonized vertices and grain boundaries, new grains start to nucleate. For very coarse-grained material, then this will happen at favorably polygonized sites, and for finer-grained materials, at the sites of pre-existing grain boundaries. These new small grains have extremely low dislocation density, which translates to a significant reduction in strength and increased ductility of the metal overall. This depends on the degree to which recrystallization takes place. From this point, these nucleated grains continue to grow. The mechanism for this reordering is diffusive. Atoms from one side of the grain boundary with a higher dislocation density move diffusively to join the new lower dislocation density grains growing, as I depicted on the bottom here. The basis for this proceeding is to drive down the overall energy associated with interfaces between grains, that is, grain boundaries. The fewer number of grains for a given area means less boundaries, and therefore smaller grains are consumed by larger ones. If the underlying system takes advantage of grain refinement, then the strength will decrease dramatically if this occurs. These are the three stages of a process called annealing. Number 1, recovery. When the material is first heated, the thermal energy allows dislocations to move and form boundaries of subgrains. Number 2, recrystallization. New grains with much lower dislocation densities nucleate and grow within the material. Number 3, grain growth. Newly formed grains grow in a competitive process, thus reducing grain boundary surface area. All of these processes serve to reduce the overall Gibbs energy associated with the material. For the most part, annealing is carried out statically. A component is placed in a furnace and held at a temperature well below any phase change, and then slowly cooled. Usually this is conducted to restore some ductility after plastic deformation without affecting the strength too much. Higher temperatures and longer periods of time at these temperatures will result in the latter stages of annealing. Let's look at the relative effects of each of the three regimes of annealing on some mechanical properties. The overall dislocation density can be used to explain the effects of the yield strength and ductility through an annealing process. As soon as the material starts to recrystallize, new relatively dislocation-free grains start to form, and this results in a big drop in yield strength and an accompanying new capacity for dislocation storage, a process that continues on through grain growth. A material held at a high enough temperature for a long enough period of time will recover, potentially recrystallize, and if left too long, have these newly formed grains grow. However, if one were to start deforming materials at an elevated temperature, then you could have these mechanisms occur dynamically. Therefore, these mechanisms should be classed under the broader term of restoration, so they can be used to refer to processes that go on dynamically. To be clear, annealing is a static restoration process, whereas hot rolling, for example, may incorporate one or all of the restoration mechanisms dynamically. Dynamic restoration is how many deformation processes are able to occur. This is very much the case for the manufacture of foils. Dynamic recrystallization occurs during rolling, which is how a billet of aluminium can be reduced in thickness by a few orders of magnitude. So, to recap, diffusion rates increase exponentially with increases in temperature. This is aided by a correspondingly increased number of vacant sites within the crystal lattice. This has been further exemplified by what happens to the diffusion coefficient as a function of grain size. Annealing is a process in which the effects of cold work and therefore strain hardening can be reversed. Annealing involves heating a metal or alloy above a critical temperature and holding. Grain size strengthening effect can be preserved if annealing is carried out carefully. The three stages of annealing are recovery, recrystallization, and grain growth, and these are restorative processes. These processes can occur dynamically, that is, while deformation is being imposed. These aspects of temperature-induced effects are not just for appreciating processing aspects of metals. They will also become important to understand when we get into how materials perform underneath elevated temperatures, a future topic. Until next time.